Yeah, we can start.
Sir, sir, welcome you to this uh, faculty development program on advanced optimization technique with MATLAB. So, presently we have 160 participants joined online, and few of them are also joined on the YouTube platform. There are total 470 people have registered in this faculty development program. So, all the participants, I welcome Swagatam Das sir from Indian Statistical Institute, Kolkata, to our faculty development program. Uh, Swagatam sir has earned his BE degree in Electronics and Telecommunication Engineering, ME degree with a specialization in Control Engineering, and PhD degree from Jadavpur University, India, in the year 2003, 2005, and 2009, respectively. He is currently a professor at the Electronics and Communication Science Unit of the Indian Statistical Institute, Kolkata. He is also serving as a professor in charge of Computer and Communication Science Division of his institute for the term 2024 to 26. He previously held the position of professor and deputy director at the Institute of Advancing Intelligence, Kolkata. His research interests comprise of deep learning, non-convex optimization, and he has published over 400 research articles in peer-reviewed journal and uh, international conferences. And Professor Das is the founding editor-in-chief of Swarm and Evolutionary Competition, a very reputed journal of Elsevier. He has served and currently serving as associate editor of several prominent journals, including IEEE Transaction on Neural Network and Learning System, IEEE Transaction on Cybernetics, IEEE Transaction on Evolutionary Competition, Pattern Recognition Elsevier, Neurocomputing Elsevier, Information Science Elsevier, IEEE Transaction of System Man and Cybernetics, and many other. He is a member of editorial board of Information Fusion, Progress in Artificial Intelligence Springer, Applied Soft Computing Elsevier, Engineering Application of Artificial Intelligence Elsevier. He has received 34,500 Google Scholar citation with H index of 88. That signifies he is one of the top researcher of our country, and he has been actively participated as various program committees and organizing committees of various international conferences. Sir is recognized all over the world. He is serving as ACM Distinguished Speaker also, and there are many awards to his credential. Uh, so, with this formal note of introduction, I request Swagatam Das sir to start his lecture today.
Thank you, Professor Nanda. Is my screen visible? Can you just confirm you can see the
Yes,
screen?
sir. Yes, sir. I can see the screen. Sir,
Okay.
here, as there are large number of participants throughout the country has joined this program, we have given option and them to chart the thing. So you can continue your lecture for complete thing, and at the end we can take the questions from the chat box when your lecture will be complete.
Okay. Thank you. And in next 1 hour or so, I am going to elaborate on the role of statistical testing while comparing and contrasting swarm and evolutionary computing algorithms, which together we can call metaheuristics for continuous real parameter optimization. And this talk describes through these bulleted points. First, the benchmarking theory of swarm and evolutionary metaheuristics. We will take a bird's eye view of how to properly compare these algorithms. some performance measures and issues, and finally we will land up to the non-parametric statistical test procedures, relevance to meta-heuristic research, statistical characterization of the parameterized heuristics, and finally some future research issues that need the attention of young researchers like you. The talk is largely based on this particular paper published by myself and my colleagues in Swarm and Evolutionary Computation Journal. And you can see another book on the right-hand side, just volume 1, but volume 2 is also there. It's an authored book on the deeper understanding of evolutionary computing, especially the exploration, exploitation, parameter control, and statistical validation. Okay. So as we know, if you look at any swarm intelligence-based optimizer or meta-heuristic optimizer, you first start with designing a representation of the problem, how you would like to encode the solutions, maybe as some particles moving in a multidimensional space, or by using some vector representation indicating real coded chromosomes, etc. Then you'd like to design a way of evaluating these trial solutions or search agents, personifying them, we can call them search agents. Then you would like to have some suitable variation or perturbation operators to change the location of these agents. These operations may be following a birth and death process like we do in an evolutionary computing technique, or the operations may follow a dynamics where some velocity is added with the current position to get the new position, as we do in particle swarm optimization and similar techniques. We need to decide how to start the initialization method, which most often could be a random uniform randomization, but it could also start from some more informed set of initial solutions. And then finally, you need to decide how to stop for the termination criteria. Usually, when we propose a new algorithm to solve a particular problem, we should avoid introducing lots of ad hoc and heuristic control parameters for that particular process, the tuning of which may not be that, that direct. So this is, for example, a problem formulation example of designing 2D infinite impulse response filters or IIR filters. If we have to minimize this J is the cost function of which is basically a difference between the desired response of the filter and actual response of the filter in some two-dimensional Fourier frequency space. And this H, Z1, Z2 is the Z-transformed prototype transfer function of the filter. We have to obey certain constraints given in the next line. These constraints assure stability of the filter. So if you look at this expression of H, these are the parameters, these are the search variables that we need to optimize, P, I, J, Q, K, R, K, S, K. If we have only two blocks, that means capital N is equal to 2, then the solution vector for this particular problem is a vector like this. And this vector itself needs to be optimized by using maybe a swarm algorithm or a real coded GA, etc. These coefficients take real numbered values. So every simulation-driven optimizer, what people usually work in the field of swarm intelligence or evolutionary computing are simulation-based optimizers, multi-variable, multi-dimensional, population-based optimizers. Whenever you propose such an optimizer, it must go through a series of acid tests on well-accepted benchmark suits. And before the method could be applied to solve real-world problems. So the primary purpose of such benchmarking is literally to identify what type of problems are most suitable to be solved by certain class of algorithms. That means we desire to have an algorithm to problem mapping. Then we also try to find out the most suitable control parameter values that boosts up the performance of an optimization technique on a specific problem by, you know, solving a number of related benchmark problems. Benchmark functions, therefore, must capture various complex aspects and features of the real world problems, because finally the optimization technique has to be done on real world problems. So benchmarking theory says through these benchmark experiments, we have to seek answers to two main questions. Given a set of comparison results across various functions, what is the best algorithm, and how can we map the benchmarking results onto the real world scenarios? Sometimes we could also seek the way of achieving a good algorithm to problem matching. As I said, you can know more about the optimization function, the function to be optimized, the landscape of the function, how it looks like, through a method called exploratory landscape analysis, which is a part of benchmarking as well. So the steps involved in any benchmarking experiment is like this. You define a problem domain, which could be single objective, multi-objective, dynamic, noisy, etc. Choose n test functions, choose p performance measures, and k algorithms to compare. Then you run all the algorithms on all the test functions multiple times, gather the performance measure values, find the consensus, analyze the results. Then you have to check what is the best algorithm. You can either individually rank them when the performance of algorithm A is better than algorithm B. This ranking should be reflexive and antisymmetric, or you can do a consensus ranking. Okay, so this is overall the benchmarking procedure. And there are various ways of enhancing the benchmarking on different types of benchmarking functions, which are also called, model functions or toy functions, representing different difficulties of the real world problems like multimodality, multiple peaks and valleys, separability, scalability, global structure, ill conditioning. These are different hard features of real world problems that need to be present in a benchmarking experiment. I will not elaborate on this part. For example, separable means can we break the original function additively into multiple functions of a single dimension, and extremely simple, like x1 squared plus x2 squared, the sphere function. You could think it as a sum of two functions, x1 squared, fx1 equal to x1 squared, and fx2 equal to x2 squared. And each of these functions can then be separately optimized. That means you can go towards the origin, which is the optimum of this problem, by along each of the coordinate axes individually. How the constant cost contours of separable and non-separable problems look like, etc., etc. Ill-conditioned problems, which are extremely sensitive to any one particular dimension. If you change, let's say, any xi by 1%, the function can change by 1000%. So if such a sensitivity is there to certain dimensions for the problem, then we call that ill-conditioned problem. And for ill-conditioned problems, the optima may lie here, whereas these curves indicate the contours along which value of the function remains constant. And this is an example function which is extremely ill-conditioned from the IEEE Congress on Evolutionary Computation, or CEC 2005 competition. So I will skip some of this. And modern benchmark suits include the IEEE CEC series of real parameter optimization suits, and also IEEE, and it started 20 years back from now, in 2005. Also, we did one competition in IEEE CEC 2011. That was a competition on testing evolutionary algorithms on real-world numerical optimization problems, gathered from various areas like optimal control, antenna design, spacecraft trajectory optimization. So all those problems, each of the problem is a single objective real world real parameter or floating point from a vector function that you need to optimize. Similarly, the Gecko conference series introduced BBOB, black box optimization benchmarking, and they also include very homogeneously distributed set of functions, toy functions or benchmark functions that cover various aspects of difficulties of the real world optimization problems. Okay. So, and then we need to keep the experimental conditions fair. Basic rule is use this when you are running two algorithms, use the same computational limit for each competitor. Allow each algorithm to use same number of not iterations but function evaluations. How many times you evaluate the cost function? Look at that. Even now I see in some of the evolutionary computing papers you compare algorithms by and plot the curve graphs of their convergence characteristics by using number of iterations as a measure of time, which is extremely wrong because uh, every one iteration of GA and one iteration of PSO do not do same amount of task. They have different internal loops, right? Also, if you allow for same number of evaluations, you should be aware of the hidden labor. For example, in some heuristic mutation operators, there may be distance function being used. Computing pairwise distances is a huge, painstaking, and computationally heavy task. You should also be aware of possibly fewer evaluations by smart operators in some algorithms. Also, when you are comparing two different algorithms or three different algorithms on particular real world or benchmark problem, all the algorithms, if they have similar population sizes, I mean, I am comparing PSO variant 1 against PSO variant 2 against PSO variant 3. So all these PSO variants should start from the same initial population. In each run. So in each run, it should start from the same initial population. Initial population must be same so that any difference in their performance may be attributed to their internal search operators only. It could so happen that if the populations are different in one population, initial population, if solution very close to the actual optimum is accidentally present. If that happens, then that particular algorithm becomes very lucky. And as a result, you give an undue advantage to one of the algorithms that you compare against others. So that must be avoided. Performance measures should also be designed to be quantitative, well interpretable with a meaning, relevant in the real world, and so on. These are some of the performance measures we usually use: average best fitness and standard deviation, best of the run fitness. So usually what we do is we run the algorithm multiple times because all these meta heuristics involve random numbers. If you run it repeatedly twice on the same problem, you will get two different answers. So what we do is on the same problem, same function, we run the algorithm maybe 30 times or 50 times or 100 times, each time with a different random initialization. If you run three variants of PSO each 25 times on the same problem, then each of these runs of the three algorithms should start with the same population, same initialization, but the initialization should change across the runs, please. Then each run will continue for a given number of iterations. Okay. After these designated number of iterations in each run, you get the best fitness value or the best function value. And that best function value that you got, 25 times you got it over 25 runs, you can get the average of that and you can get the standard deviation of that. If you already know what is the optimal function value f of x star, then you can take the difference between fx and f of x star, that is the error. And then the best of the run error you can save. You can average 25 or 30 or how many times you run that on that all the runs, you can average this best of the run error and report. Then you can, so, and standard deviation, if the standard deviation is small, that means your algorithm is a robust algorithm. It is giving very similar results on repeated runs, right? This is very important. So, and similarly, success rate. You can assume that you need to get to a threshold value of the error. You need to get to maybe, let's say, if your tolerance is 10 power minus 2 for the error, that means error value, I will continue to run the algorithm until I reach the error value equal to 0.01, or my designated maximum number of iterations is exceeded. Suppose I will continue each run of my algorithm until either 1000 iterations are finished or my algorithm has reached the threshold error level of 0.01. If my algorithm reaches that threshold error level, then I will designate it as a successful run. Otherwise, it's not a successful run. So I run my algorithm 25 times, and I see that 20 times it became successful. So my success rate is 20 by 25, which is 80%. That is another measure. Success rate actually tells you how frequently your algorithm is able to get to the very close to the optimum, starting from different random initializations over a given set of runs. Okay. Convergence graphs usually show how the best function value of the population, the best error or the best fitness of the population varies across number of AFEs or number of fitness evaluations. So if you have the population size equal to 100, and if you allow it to run for 1000 iterations, if in each iteration the fitness is evaluated only once per population member, then the total number of function evaluations would be 100 into 1000. That means 1 lakh. And in evolutionary computing, we measured the time in terms of number of function evaluations or number of fitness evaluations. We call it FEs. If you look at this graph from one of my own paper, you can see we are comparing different variants of differential evolution, or DE, which is a family of very nice, very efficient global optimization techniques. And you can see all the graphs starts from the same initial point. Why? Because the initial population is the same. Initial population for all the 6 graphs is the same. If not, then your algorithm is not fair. Okay. So I will now come to the central part of it, why statistics should matter for a swarm intelligence researcher or an evolutionary computing researcher. See, whenever you are comparing the results of 2 randomized algorithms, 2 stochastic algorithms, the results may have the element of luck. That means you are getting very good result on a function, maybe because your initial population contains accidentally a very good solution, or because actually the difference that you are showing between the 2 algorithms is accidental instead of being original and profound. So for scientific papers where a claim is made, let's say some crossover operator like exponential crossover is better than binomial crossover, just as an example, or my PSO variant is better than your PSO variant, or my so-called new meta heuristic, my monkey optimizer is better than your donkey optimizer. If some such claim is made, okay, Nowadays, almost every day we hear new optimization techniques, which is extremely worrisome, a trend, and should not be there. But anyway, so whenever we hear such claims, they must be justified on the basis of statistical hypothesis testing. Statistical significance of the comparison implies. So, what is this hypothesis testing? What are we doing here? If I run the algorithm, let's say 50 times on a particular problem from 50 initial populations and note down 50, best of the run errors or 50 best of the run fitnesses, these 50 results are basically samples from an underlying population. Population is huge. This population is what? This population is the collection of all possible runs of the same algorithm on all possible initial solutions on that problem. And it is infinite in size, right? We are looking at 50 samples from that population. Similarly, another algorithm is run on the same problem from different initial solutions 50 times. So those 50 results are also the representative sample from another population of all possible executions of that another algorithm. Statistical hypothesis testing tries to answer the question whether these two populations are really different from each other. That means if you run these two algorithms many times, infinitely many times, and average out all those results, will they really be different from each other? Or the difference that we see, my PSO is better than their PSO, this difference that we report proudly in our paper is just a matter of accident. That is where statistical test comes. So if you look at this, how the fitness varies, fitness here this is for a maximization problem. That's why it's going up. Our PSO just happens to start near the best solution in the benchmark problem we are using, and the other PSO starts far away in the search space from the best solution. As a result, our algorithm shows a high fitness on average. Okay. Is our PSO better? This question has to be answered. The opposite can also happen. Okay. This time, due to the random nature of the swarm intelligence algorithm, it appears that the current best algorithm outperforms our algorithm. Clearly, we cannot make any comparison between SI algorithms based on individual runs. How about running several replicates of each evolutionary or swarm algorithm with different random number of seeds and show the average performance of these algorithms over time? If we do that, instead of just one execution, we are doing the average over multiple executions and showing how the average fitness varies across iterations. If the number of particles in each swarm is same, then number of iterations is just proportional to number of FEs, and we can then show it like this. But ideally, we should always show in terms of number of FEs. Because of a scale problem, we are assuming we are showing here in terms of number of generations. But the thing is, if you look at even these two curves, it looks like our algorithm is better than the current best algorithm on average over many replicates. The average fitness, now if we characterize the average fitness and its standard deviation over a 95% confidence interval, which is a statistical term, now this graph shows that our algorithm does not actually perform better than the current best algorithm, because the 95% confidence intervals are quite overlapping. Okay, against each value, the 95% confidence intervals are quite overlapping. And that means the two algorithms are performing similarly. So these such statistical characterizations are important to validate your result and publish your paper. If you do not give them, your paper will should simply be rejected. So Naturally, first let me give you an example of non-statistical hypothesis testing. Suppose a criminal trial is going on in the courtroom, and there is a judge or a jury panel who have to decide between two hypotheses. The null hypothesis is H0, the defendant is innocent, and the alternative hypothesis is H1, that is, the defendant is guilty. And null hypothesis is basically a statement about the property of some population, the parameter of some population, and this statement needs to be supported by suitable evidences. Okay. Null hypothesis is usually a statement which remains by default true. So, for example, uh, in Indian judiciary, we believe in innocent until proven guilty. So H0, the null hypothesis is the defendant is innocent. On the other hand, the alternative hypothesis or research hypothesis is H1, which is the defendant is guilty. So the jury doesn't know which hypothesis is true. They must make a decision on the basis of the evidences presented. Similarly, while comparing two sets of results from algorithm A and results from algorithm B, algorithm A, we have 50 results. Algorithm B, we have 50 results over 50 runs. These results are actually samples from an underlying population of all possible executions of that algorithm on that problem. So in this case, we have two underlying populations, and our null hypothesis is basically that the population locations or the population properties are same. That means there is no difference between the two algorithms over a large scale. And the alternative hypothesis is that, so you see, alternative hypothesis is that hypothesis. It's also called the research hypothesis that people have to prove. Why it is research hypothesis? Because police and detectives must do a lot of research, gather evidences to prove that the defendant is guilty. In Indian judiciary, if you do not do that, then by default, the defendant is innocent and the defendant will be acquitted. Okay. Similarly, here, the alternative hypothesis is that the locations differ. Population 1 is located to the right of population 2 or to the left of population 2. That could also be another alternative hypothesis. Alternative hypothesis number 1 just says, okay, the two populations are different. This is called non-directional alternative hypothesis. And if we say population 1 is on the right of population 2 or left of population 2, or population 1's parameter is greater than that of population 2 or lesser than that of population 2, then we call it a directional alternative hypothesis. So the entire inferential statistics is concerned about this situation. We have two populations. Population is characterized by some parameters like mu. Mu might be the mean of the population, mean best fitness of all possible executions of an algorithm on a particular problem. That is mu. And we have a sample. Sample means 50 runs that you have done on your machine and noted down the results. This 50 runs is a mean. So is your sample set, and the sample mean is basically the average fitness over your 50 runs. So your population could be the entire population of India, and one property of the population could be the average body weight of male Indian population. Okay. Now I cannot go to so many people and ask their body weight. So what we do is we sample only 300 or 1000 people from different social strata, note down their body weights. So that then we average all these 1000 body weights and get X bar. And the original average body weight of Indian people is mu. Now we have to see how close is X bar to mu and how we can compare. So Indian people's body weight versus USA people body weight. You got 1000 samples from India, that average is X1 bar. 1000 samples from USA, that average is X2 bar. And the original average body weights of the two populations are mu1 and mu2. Now you will tell me by looking at x1 bar and x2 bar, you will tell me whether mu1 and mu2 are really different from each other or they are very close to each other. This is just an example of what we do in such two-sample hypothesis testing. And every evolutionary computing algorithm's result must be backed up by such tests. Okay. So a statistic is literally some property of the sample set. Sample mean is a statistic. And standard error, for example, standard error of mean or standard error is literally the standard deviation of the mean itself. So if you vary you are collecting samples. Sample mean is x bar. If you collect different samples at different times, then the x bar will also vary. Now, in statistics, the central limit theorem and law of large number permit us to assume that for large sample sizes, these x bars follow almost approximately a normal distribution or Gaussian distribution. So, a statistic is the standard deviation of its sampling distribution. Sampling distribution means distribution of the mean x bar. And if the parameter or the statistic is a mean, then this standard deviation of that particular statistic, which is the sample mean, is known as the standard error of mean or SEM. If the original population's standard deviation is sigma, and the number of entities in your sample set is n, that means sample size is n, then the standard error of mean is sigma by root n. Confidence interval is basically an estimate computed from the statistics of the observed data that might contain the true value of the unknown population parameter. So the true value of the unknown population parameter, 95% confidence interval is, suppose you are estimating some fitness value to be 3 and your 95% confidence interval is 1. That means the true value of that parameter, which you estimated as 3, will lie between 3 plus 1 and 3 minus 1 with a 95% chance. That means the true value will lie between 4 and 2. You have estimated it as 3, but it may not be exactly 3. It may be 3.6 or 2.9, but it will lie between 2 and 4 with a 95% probability. That is called 95% CI or confidence interval. So we want to compare the performance of two algorithms. All we have to do is to check whether the algorithm's 95% confidence intervals overlap. If they don't, then we are confident that our PSO performs significantly better than the current best known PSO, at least 95% of the time. So that means here, if you look at this, if the 95% confidence intervals overlap to this extent, that means the true fitness of the blue algorithm and the green algorithm may appear at the same position. They may not differ at all. But if they really differ from each other, they do not overlap, then we are confident. So the test statistic is the most important thing in hypothesis testing. It is a standardized value that is calculated from the sample data during the hypothesis test. And then by using standard normal curve, from the test statistic, we calculate something called p-value. This p-value literally is the probability of the null hypothesis being true. If p-value is very small in your test, less than 0.01 usually, then you can be confident enough that your null hypothesis is not true. That means the two populations are quite different from each other. That means if you are having on average good result in your PSO than their PSO, then that good result is really statistically significantly better, provided this p-value is very small. P-value is literally showing you the evidence in favor of the assumptions of null hypothesis. So if you look at just one sample Z test, which is literally you have a population, the population's mean is mu, you are assuming your null hypothesis is average body weight of all Indian people is let's say 74 kg. So your null hypothesis is mu equal to mu naught. This mu naught may be a numerical value like 74 kg. And your alternative hypothesis is the average body weight is not equal to 74 kg, or it is less than 74 kg or greater than 74 kg. Then you calculate a sample of Indian people, calculate their average body weight, which is X bar, subtract this mu naught from X bar and divide by the standard error of mean around X bar. That means the standard deviation of the sample set, which is sigma by root n, and calculate this test statistic, which is Z stat. And then the law of large numbers tells us that this Z stat follows a standard normal distribution with mean 0 and standard deviation 1. By looking at the standard normal curve, find out the area which is beyond Z equal to Z stat. And on the other side, for Z less than minus Z stat, then you can look at these two areas and find out the p-value therefrom. And from the p-value, you can interpret whether your null hypothesis is true or not. So p-value answers the question, what is the probability of the observed test statistic when null hypothesis is true? So smaller and smaller p-values provided stronger and stronger evidence against the null hypothesis. So if the p-value is less than certain threshold level, which we call significance level alpha, that is a strong evidence. So essentially, suppose your null hypothesis is mu, the average body weight of Indian population is 74 kg. You got a population, you got a sample set of 100 people, average their body weight, and your body weight comes out to be 90 kg. So then the area beyond Z stat will be very small actually. The test statistic will become something which gives you a very small p-value, 0.001 or something like that. And the p-value answers the question that if really the population's average body weight is 74 kg, the probability that in any random sample of 100 people I observe the average body weight of 90 kg is extremely small, very small. So that indicates the original population cannot have average body weight of 74 kg. It must have shifted. Okay, that is how the one sample tests work. Now, usually such parametric statistical tests assume the their underlying assumption is X bar, the population mean, will follow a parametric distribution, which is like the normal distribution or Gaussian distribution. This is true only when we have large number of samples, 50 or 100. So, but nowadays we don't have the time of running an algorithm 100 times and getting 100 sample runs. So what we do is, so parametric tests are like t-tests, z-test, one sample z-test I just mentioned, chi-square, ANOVA, these are all parametric tests, which assumes that the data is coming from an underlying population which has a normal distribution. Similar variances for too few data points, similar sized group of data points, and cannot be more reliable if the assumptions are true. But if the assumptions are false, if you are only talking about 10, 20, 30 samples, then non-parametric tests like the Wilcoxon's rank sum test or Kruskal-Wallis H test, Friedman's FR test, such tests have to be taken into consideration. Wilcoxon's rank sum test is the best one for comparing two evolutionary algorithms. It's also the non-parametric counterpart of two sample z-test or t-test. Under this test, instead of two population means, two population medians are compared. Okay, so our test statistic is not the mean of the sample, but the median. So what we do is, suppose N1 and N2 are the number of independent runs of two evolutionary algorithms, denoted as EA1 and EA2. Then we have sets of N1 best of the run objective function values for EA1 and N2 best of the run objective function values for EA2. Total number of results is N1 plus N2. Although we are dealing with two sets of results, we can rank all these N1 plus N2 according to the values of these objective functions, and smaller means better. Smallest objective function will have rank 1, because suppose we are dealing with a minimization problem. So then we will work with the ranks instead of the numerical outcomes, and then the sum of the ranks in any one of the group of these results, denoted as W, now will serve as the Wilcoxon's rank sum test statistic. Why and what is the underlying mathematics behind it is very large. I'm not going into that. This is not it's out of the scope, but let me tell you, here we collected two samples. We combine them to have N1 plus N2. The sample sizes need not be same, unlike the Z test, two sample Z test or parametric tests. So we have two samples. They can have different sizes. We merge them. We rank all of these results, and then sum of any one group of results is called the test statistic W. Then we find out in terms of N1, N2, and capital N, which is N1 plus N2. Statistically, we can derive that this W is also a random variable. This W will have a mean and a standard deviation, mu W and sigma W. We can find these values out, and then we can again standardize the value of W by using this mu W and sigma W, assuming that we get Z values, and these Z values will now obey a standard normal distribution. By looking at the standard normal curve using a software, we can calculate the corresponding P values. Let's take an example from my own paper, long back though. So in this paper, we are comparing one algorithm, DEGL, which is our proposal, against a baseline D algorithm, D rand 1 bin, on a 30-dimensional Grewonks benchmark function, 10 times. So we have 10 results for DEGL and 10 results for D rand 1 bin, two variants of differential evolution. So we have these numerical values of the objective function. We have 20 such values, so we rank them together. Our null hypothesis is that there is no difference between the results of D rand 1 bin and DEGL, and the alternative hypothesis is the results of DEGL and D rand 1 bin differ significantly. Okay. So if the results differ significantly, and if we are claiming that DEGL results are better, that means they're really better, they're significantly better. So what we do is, after we rank these, we sum up the ranks for one of these groups, let's say D rand 1 bin, and the sum is becoming 147. So I sum up all these values, 14, 16, 15, 19, all these. Mu W is 105, sigma W is 13.23, so my standardized Z value is 3.63. This Z value corresponds to a P value of Z greater than 3.63, and this P value is very small because the area in the standard normal curve beyond 3.63 is very small, 0.0008. That means we have a strong evidence to reject the null hypothesis that the two compared evolutionary algorithms are similar in performance. They are actually very dissimilar. So sum of the ranks is very important, because when we have two such populations, and if we draw samples from these two populations like this, If the locations of the two populations are about the same, that means the null hypothesis is true. We would expect the ranks to be evenly spread between the samples. So sum of the ranks of the purple population is 37 and that of the green population is 41. Now, if the green population shift to the left of the purple population like this, initially the sum of the ranks were like this. Now there is a shift, so the ranks change. The green sample is expected to shift to the left too. As a result, several observations exchange locations. What now happens to the ranks? You see, some of the ranks, because of this interchange, some of the ranks is also varying. The green sum decreases, the purple sum increases, changing the relative location of the two populations. That means which population is having better results and which population is having worse results. If you change that, then some of the ranks of the two populations, two samples combined, will also change. So among the non-parametric hypothesis testing procedures, we have for pairwise comparisons between two algorithms at a time. We can do Wilcoxon's rank sum test or Wilcoxon's signed rank test. Signed rank test assumes that all the results are coming from same initial population. Mind it, all results are coming from same initial population. Then we can have multiple comparisons against a control method. You can compare 3 or more methods, treating one of them as a control method. And on a single problem instance, the examples are, so one problem, multiple methods. One problem, two methods, you are going to use Wilcoxon's rank sum test or signed rank test. One problem, multiple methods, you should use Friedman test, Friedman's aligned rank test, Eman-Davenport test, Quade test. All these tests are available as small Python packages or by using customized software, online software calculators. Multiple, so ultimately you will report the p-value. P-values would be returned by program, but I tried to convey to you what you are doing. Nowadays, people do all these experiments without knowing what they're doing and how to interpret, which is very, very bad. Then you can also do multiple comparisons among all methods, multiple problems, multiple algorithms. You can compare them, and the appropriate statistical tests for this situation are the Bonferroni-Dunn test, Hochebox test, Nemaini procedure, and so on. This is, for example, the Bonferroni-Dunn test. Several D and PSO variants have been compared. It is from one of our paper. And this control method is here. Control method's performance is, this is the CD control method at 2.04. And we are ranking the results from other algorithms. So a rank which is much less than the control algorithm, this control value implies best algorithm actually. So these are two excellent resources, of which this resource I already pointed out, two excellent resources and some statistical calculators. In fact, you can use some of these using Microsoft Excel, etc. also. So are the search moves in swarm intelligence algorithms really different? General random walk-based system of equations is used in swarm intelligence. You have the current position xi and you are adding a scaled version of the perturbation with that xi. Meta-heuristics usually differ in terms of the methods of determining the step size s and the direction delta x. So for example, in classical ABC, we have this sort of search equations. And differential evolution, in fact, the RAND1 mutation is also very similar. If you select the crossover rate CR equal to 1, it's exactly the same. Or CR equal to 0 will also be the same for just one single component perturbation. Very often, the new variants show striking similarity. The G-based guided ABC algorithm is very much similar to D target to best one. And there are lots and lots of such examples. For example, the cuckoo search with Levy flight has a close resemblance with evolutionary programming based on Levy flight, which was published 8-9 years back than the cuckoo search paper. So, and many such things can appear. Chemotaxis in bacterial foraging optimization is a variant of the stochastic hill climbing local search. Elimination dispersal phase of bacterial foraging is very similar to the start mechanisms in EAs. The philosophy of attraction towards the best solution continues to creep in the perturbation strategy of most of these swarm intelligence algorithms, PSO, GSO, ABC, D, GA, chicken swarm optimization. I'm just listing a few. Cat swarm optimization. These are extremely similar to PSO with adaptive acceleration coefficient or global only PSO model. There is a PSO method. If you go on benchmarking these methods, the new so-called new meta heuristics on the basis of statistical tests like Bonferroni-Dunn test, you will see that most of these algorithms like GSO, ABC, Cuckoo Search, Firefly, then there comes the teaching learning, Jaya, all these algorithms. If you benchmark them on a really tough benchmark system like CEC 2005, you will see that their performances, those ranks which are above the CD in Bonferroni-Dunn test, these algorithms are statistically similar. Their results are not very different, and on the other hand, these algorithms, which are literally the advanced variants of PSO, DE, etc., these results are quite different from these so-called new algorithms. Nowadays, this is a very bad trend, and this has diluted the field of evolutionary computation to a large extent, that we are almost getting inspiration from almost all natural methods and designing an optimization technique which is basically repackaging the old known search moves and search techniques from classical algorithmic families like PSO, DE, real coded GA, evolution strategies, etc. And we are repackaging it in the name of a new algorithm without scientific and statistical benchmarking process, just for the sake of publishing yet another paper. This trend must be stopped. And to stop it, you must know what should be the best way of designing an efficient heuristics, how you can achieve the good trade-off between exploitation and exploration, how you should not impose serious computational overheads, should not have several algorithmic computer control parameters, except for a very few and indispensable one. Also, you should put your ideas in a metaphor-free language. So, for example, this is one table from one of our papers where we are showing how the metaphoric language in different bee foraging based algorithms are actually decoded, deciphered. For example, queen and drone are candidate solutions. Workers are local search heuristics. Food sources for ABC algorithm by Karaboga et al. Are basically candidate solution. Nectar amount means fitness value of a solution. So when you are writing an algorithmic paper, call a trial solution a trial solution. Don't call it a particle, a bird, a chicken, an egg. Don't call those things so foolishly. That dilutes science. Don't call it fitness value as nectar amount or amount of water in water drop optimization and all those stuff. Be direct. So looking into the future, so many algorithms, so little time. Inspiration for designing optimizer are coming from diverse sources, ranging from human society to flu virus. There is a coronavirus inspired algorithm also. Why? Because everyone wants to be a pioneer in this extremely diluted field. Are these numerous algorithms really effective? Will they survive in the long run and in the face of challenges posed by real world problems, or will their influence remain largely confined within the world of paper writing? Do we really need yet another ABC or PSO or GWO with a marginally better performance over a set of non standard benchmark functions? Or is it the time to look more into problem-specific research on and with evolutionary algorithms? For example, if you look at this particular paper, it doesn't propose any new algorithm, but it says for the protein folding problem, AB of lattice protein structure prediction problem, how the optimization landscape looks like and what algorithms would be befitting. This was in 2017, long before this AlphaFold for protein structure prediction was devised. So similarly, so these are some of the areas where we need trust. We should design and study the similarity between different benchmarks and the corresponding real world problems. For example, the Talk design problem has striking similarity with the 6-hump camelback function. FM sound wave synthesis is a real world problem from communication engineering. The objective function has great similarity with the 2D inverted Schubert function, which is a standard benchmark. Radar polyphase code design, you see, this is a communication engineering problem. How similar it is to the composition function from Suganthan's CEC benchmark. So such similarities help us to know, okay, if on this benchmark, this particular algorithm is doing good, it will do good on the real world problem also. Okay. So such studies are much more important, and these studies require mathematical knowledge of the statistical benchmarking procedure, instead of just looking at a random natural event and is coming up with an optimizer. Thank you very much. I will stop here. If you let me see if you have any questions on your chat, I will be happy to answer.
So I request participants to write in the chat box whatever doubts they have. Sir, can you able to look at the chat box?
Yeah. So could you tell me the difference between maximum iterations and function evaluations while running an algorithm? We usually write the command as, see, if your number of, suppose your population size is 40 and your maximum number of iterations is 1000. If your algorithm ensures that in each iteration you are, for each candidate solution, you are evaluating the fitness function only once, then your number of fitness evaluations is equal to 40 into 1000. So usually, if you are not evaluating your fitness function for each trial solution of the population more than once, then the maximum number of iterations into population size gives you the maximum number of FEs or fitness evaluations. Okay. So function evaluations could be calculated by using just an extra line inside through this multiplication. But you must see whether some algorithms are there, especially in these artificial bee and other places, where for each population member, you may have to calculate this fitness function 2 times in each iteration. You must not do that. So if not, then there is a simple multiplicative relationship. Okay. Any other question? How to validate the obtained best results for random problems? What do you mean by random problems? You have some problems and you are using your algorithm, you are running your algorithm, suppose 30 times on that problem. You got 30 times means 30 runs. Each run goes up to a maximum number of fitness function evaluations. So you got 30 such best of the run values. You take their average and their standard deviation, then you do a statistical hypothesis testing if you want to compare it against another algorithm's results. That is where the statistical hypothesis testing will say If your average is just better than their average, whether this betterment is statistically valid or not, that will be given to you by the statistical hypothesis testing. Usually, for all evolutionary algorithms, result of a single run signifies nothing. You have to run it 30, 40 times. You have to look into the standard deviation, and then you have to perform statistical hypothesis testing to validate your results. Okay. Okay, so another question is here. If I use function evaluations instead of maximum iterations, what will happen to the algorithm? Nothing. As I said, I mean, function evaluations you can use to draw the convergence characteristics, and from number of function evaluations, you can derive the number of iterations actually. Suppose you have your population size is 80 and your number of function evaluations is 8,000. If you are using per solution only once fitness is evaluated in each iteration, then your number of iterations would be equal to number of function evaluations 8,000 divided by population size 8. That will give you 100, and that's it. So you can always back calculate, but my point is when you are plotting the convergence characteristics across different algorithms, some of which may not evaluate the fitness value only once per iteration. So for all such general comparisons, the x-axis of your graph, the time axis of your graph should be plotted in terms of number of function evaluations and not in terms of number of iterations. That is more scientific. Okay, how parameters, population size and number of iterations were chosen and their impact on the algorithm's performance would be valuable. Okay. So see, population size usually for differential evolution, most often we take it to be 100. If the population size is very high, then computational overhead associated with each iteration would also be very, very high. So, and for PSO, particle storm optimization and similar algorithms, 40 is the standard size. But the rule of thumb would be if you have your dimensionality of your problem, the number of dimensions that you are optimizing, if that dimensionality is D, then the population size should be 5D for PSO and between 5D and 10D for differential evolution. That is a rule of thumb. Population size something between 40 and 50 for swarm algorithms and 100 for differential evolution and real coded GA type algorithms is nowadays a standard choice. On the other hand, maximum number of iterations that you want to choose is specified in different benchmark experiments. In CEC benchmarks, the rule is maximum number of function evaluations. They provide the stopping criteria in terms of number of function evaluations, and that number is 10 to the power 4 into capital D, where capital D is the dimensionality of the problem. That means whether it's a 100D function or 10-dimensional function or 30-dimensional function, it's always D times 10 power 4 maximum number of FEs or fitness evaluations. And if you divide these fitness evaluations with the population size, and as per the condition I mentioned, then your number of iterations you get. Usually these are problem dependent, but for benchmarking, the benchmark functions have their own protocols and they clearly mention what you should choose as your maximum number of iterations. The population size depends on the algorithm. And definitely, I told you the standard practices in these major algorithmic families. Rajashekhar, this is very simple. I mean, you have a random set of, suppose you want to compare three algorithms, and for all three of them, the population size is 40, three PSO variants. So for each run, you create 40 random solutions only once. Now distribute those 40 random solutions to algorithm 1, give the same random solutions to algorithm 2, and give the same random solutions to algorithm 3, and start their execution. In the next run, you again initialize 40 random solutions and give those same 40 random solutions to each of these three algorithms. That's how you go on. That means in each run, you are starting the execution of these algorithms from the same random solutions. So any difference in their performance must be due to their internal operators, not because one algorithm got very lucky by having a very nice initial solution, not because of that, right? Thank you, everyone. If there are no more questions, then we can possibly end it up. Namaskar.
Thank you, Swagatam sir, for enlightening us with various statistical tests and the design of meta-heuristic algorithms, their pros and cons. And we have another session from you on the dynamic and constant optimization on next Friday. So I request participants all to join also in that particular session of Swagatam sir. So thank you, sir.
Okay, okay, bye.